To a course on complex analysis. In the previous lecture, we have started our discussions on the concept of antiderivatives. We have just stated the theorem on antiderivatives and we have seen some examples. As a continuation to the previous lecture, we are going to see few more examples and we will start proving the theorem that we stated. We have seen till this example in the previous lecture, right? Now we will begin the next one, that is we are about to see the next example. Okay, here let us consider, let's see one, denote the right half z equals 2 e to the power iota times of theta. We are again considering the same thing in the right half, that is minus pi upon 2 less than or equals theta less than or equals pi upon 2. So we are considering this way. We are considering the right half of the circle, circle what, that is z equals 2 e to the power iota times of theta. Exactly the same circle that we have considered in the previous example is considered here. In that circle we are taking only the right half, right? So the principal branch, what is the principal branch, that is log z equals ln r plus iota times of theta with r positive, theta lie between 0 and pi. Okay, this principal branch is going to serve as the, this is the principal branch of log function, serves as an antiderivative derivative of 1 upon z in the evaluation of integral over c1 1 upon z dz along this thing. Okay, so this is going to serve here. If you notice, the part that we have considered is uh, this is the part that we have considered. So minus 2i to 2i is the limit in this direction we have considered. From, it is clearly specified that from minus pi by 2 to pi by 2 is the thing that we have considered in this example, right? So if you see integral over c1, your dz upon c is going to be integral minus 2i to 2i dz upon z. So it is what? It is principal branch. Okay, this is going to serve you as your antiderivative. That is what we have said. From minus 2i to 2i. So if you substitute those values, log 2i minus log minus 2i. So what is this? This is ln 2 plus iota times of pi upon 2. Okay, this quantity minus ln 2 minus iota times of pi upon 2. So ln 2 gets cancelled and we will be left with what? Iota times of pi upon 2 plus iota times of pi upon 2. This simply turns to be pi I. Right? Now let us consider, let C2 denote the left half, that is z equals 2 e to the power iota times of theta with theta lie between pi by 2 to 3 pi by 2 of the same circle. Okay, which means here also the same thing is going to happen here. we'll have to consider the branch log z equals ln r plus iota times of theta with r positive and theta lie between 0 to 2 pi, okay, of the logarithmic function. This branch we are considering here. This is going to serve as an antiderivative. Okay, integral over c2 dz upon z is integral. Here, if you draw and see what is the diagram here, you can very well notice that it is going to be, okay. So this is your c2. Again from 2i, this is from 2i to minus 2i, right? So if you just plug in these informations into it, it is integral from 2i to minus 2i dz upon z. It is log z 2i to 2i minus 2i. So it is log of minus 2i minus log 2i. Okay, we find the values. It is log 2 plus iota times of. Now we will have to see theta value lie between pi by 2 to 3 pi by 2. So basically here, how do we write this one? So let me give you that ideologies. We have already seen log z. Suppose if z takes the form x plus iota times of y, then this is half times of ln x squared plus y squared, that is r. Okay, uh, plus iota times of tan inverse of y upon x. Okay, this may be any quantity. If we write this as theta, this theta can take any value in this interval. Okay, it may be inside any interval of length 2 pi. Here we have very well specified the value of theta must be in this interval. Okay, so this is what we take it as, this quantity we take it as theta, and this theta value has to be in this interval pi by 2 to 3 pi by 2. I think I have made some mistake. Yeah, okay, so this is the case. Yeah, there is no mistake. This is the case we are considering right now. Now if you do here, either you may write this way or you may write this way. Here for minus 2i, what is going to happen? For minus 2i, your x value is 0 and y value is 2. So under root minus 2 whole squared, which is simply 2. Right? Okay then. So next, tan inverse of y upon x. What is y here? This is minus 2 upon 0. So tan inverse of this quantity. So we take this to be minus infinity, right? So we can consider this to be minus infinity. So tan inverse of minus infinity. If it is tan inverse of infinity, we write that as pi upon 2. Since it is, this goes like this and this comes like this. So we consider this as 3 pi by 2 in this. Actually, tan inverse of this quantity, right? That is tan inverse of minus infinity. We consider this as 3 pi upon 2. Okay, so as it reaches pi by 2, it goes like this. Again, after pi by 2, it starts from here and comes like this. So when it is 3 pi by 2, it is somewhere like this. Okay, we are considering that way. And if you come here, it is what? Tan inverse of 2 upon 0, for which we consider this as pi upon 2. Okay, so here we are going to have this as iota times of 3 pi upon 2 minus log 2 plus iota times of pi upon 2. Okay, this is 3 pi upon 2 minus pi upon 2 times of iota. So this simply gives you what? 2 pi upon 2, which is pi I. Okay, in both the cases we get this to be pi I. Now let us find out the value of the integral of the function 1 upon z around the entire circle C, which is C1 plus C2 is integral over C dz upon Z, which is integral over C1 dz upon Z plus integral over C2 dz upon Z, which is pi I plus pi I, which turns to be 2 pi I. Okay, so in the previous example, just because this given C is considered to be the closed contour, we concluded that the integral value is 0. Okay, but that cannot be the case always. That is what we were exactly trying to convey in this example. Okay, we have split the entire contour into two contours. Okay, we have split that entire thing into two different things. As a combination, we are going to get the entire circle. Based on what part of the circle we choose, we'll have to identify some antiderivative accordingly. We have chosen an antiderivative accordingly, and we evaluated the integral, and finally we found that this value around this contour turned to be 2 pi I. Right? Now let us get into the next example. That is example 4. Okay, so here we are about to evaluate. Here we are about to evaluate integral over c1 z to the power 1 upon 2 dz, where the integrand is the branch. Here, what do we mean by the integrand? The function which is to be integrated in the given problem is called as integrand. Okay, so here this is one of the multi-valued function. We'll have to identify a suitable branch, and that branch has to be integrated. So what we are going to consider is, we consider f of z, which is z to the power half. Okay, either this may be considered in this way: exponential of log of z to the power 1 upon z. So this may be written as exponential of half times of log z. It may be written like this. Okay, after writing like this, we can give the notations, like we shall write this as in the principal format or in any general format. So logarithm of complex quantity we have, right? So half times of, okay, let me use this bracket here, and this shall be written as log r plus iota times of theta. Okay, so this is what I have with what r positive and theta to lie in this interval, right? So this becomes what, exponential of half times of log r multiplied with exponential of half times of iota times of theta. So this is exponential of log r to the power 1 upon 2 multiplied with exponential of iota times of theta upon 2. So this may be written as under root r e to the power iota times of theta upon 2, with what, r positive and theta to lie between 0 to 2 pi. Okay, so we consider this part. Okay, this branch of the integrand is to be considered. Okay, which is where the integrand is the branch of the square root function, and c1 is any contour from z equals minus 3 to z equals 3. Okay, here we are actually here we are just asked to evaluate the integral over what. That is what I am saying. I am just stating the question here, right? I am not entering into the solution part of this example as of now. I am just stating the questions. Okay, in the question itself I am just explaining few things. This that except for its endpoints lies above the x-axis. Okay, which means here you are having some sort of a function. You will have to identify what is z is equals minus 3 and z is equals 3, except at this end points this completely lies above the x-axis. Okay, this is your c1. Okay, it is evident. Fine, this is what is given, right? Now we know that if a contour means that has to be piecewise smoother. Okay, here the integrand is also a piecewise continuous function on the given contour. Therefore the integral value can be found. That is what I said is given integrand z to the power half is piecewise continuous on c1. If it is piecewise, it means it can admit only few points of discontinuity. Okay, but still this tells us integral over c1 z to the power half dz exists. This integral value exists. Okay, so here the branch that we found, let us consider this as equation 1. The branch 1 of this function is not defined on the ray theta equals 0. If you are about to consider the point theta equals 0, this means what this is the point 3 and this is minus 3. Theta equals 0 means at this point the function is not defined. Yes, we know that for sure, right? So that is what is written here. In particular, we shall say at the point z equals 3. Okay, if you are about to consider another branch, okay, I am going for another branch, so let me write that in different color. But another branch, let me write that as f1 of z, which is under root r e to the power iota times of theta upon 2 with r positive and theta to lie between minus pi by 2 to 3 pi by 2. Okay, this is defined and continuous everywhere on C1. Okay, and now we have considered two different branches of a same function. Okay, the first branch that we have considered, that is given whatsoever is given in equation 1, is not continuous at one point. Okay, since the function itself, the branch itself is not defined at that point, that is 3, the function is not continuous at that point. Whereas we have considered another branch here, that function is continuous everywhere on C1. Okay, so let me mark this as equation 2. So here, comparing equation 1 and 2, we are about to write something else. That is, the values of f1 of z at all points on C1 except z equals 3 coincides with the value of f of z in equation 1, which means these two branches share most of the values equally. Okay, the values of f of z and f1 of z are equal at all points except at z equals 3, because the previous one, the former one, is not defined at this point, whereas the later one is defined at this point. Okay, now only at one point it is missing. Now let us integrate this quantity, like let us try to identify the integrand antiderivative of f1 of z and try to with that of try to solve this problem using that. Okay, hence the integrand can be replaced by f1 of z. Here your integrand is f of z, but just because it's the values of f of z and f1 of z are equal except at this point, we can replace that with that. Okay, when you are about to integrate, you are going to make all possible things. Whether you miss only one point or not, that doesn't matter in the case of integration. Like what I'm trying to say here is, if you are integrating a function in closed interval 0 comma 3, or closed at 0 open at 3, or open at 0 closed at 3, or open at 0 closed at open at 3, you integrate this function in all these four intervals, you are going to get the same value. So exclusion of one point, that does not matter in the case of integration. Okay, this is general for real integrals as well, and those ideology is about to expand to this case. Okay, the now let us try to find out the antiderivative of this function, that is the antiderivative of f1 of z is the function big f1 of z, that happens to be 2 upon 3 z to the power 3 upon 2, that is 2 upon 3 exponential of log of z to the power 3 upon 2, and this may be written as what, exponential of 3 upon 2 log c, this is 2 upon 3 exponential of, we have this 2 upon 3 exponential of 3 upon 2 log x squared plus y squared, that is r to the power 1 upon 2, I guess so. No, simply r, right? So that is under root x squared plus y squared plus iota times of theta. This under root x squared plus y squared is r plus iota times of theta, with r positive, theta to lie between minus pi to 3 pi by 2. Okay, we have this 2 upon 3 here, and this may be written as exponential of 3 upon 2 log r multiplied with exponential of iota times of 3 pi theta upon 2. 3 theta upon 2. So this is 2 upon 3, and this shall be taken to the power, and therefore you are going to get what? Exponential of log of r to the power 3 upon 2 multiplied with exponential of 3 iota times of theta upon 2. So this is 2 upon 3 r to the power 3 upon 2 multiplied with e to the power iota times of 3 theta upon 2 with r positive, and so this is what we have found the antiderivative of this function. Now let us evaluate integral c1 z to the power 1 upon 2 dz, which is from minus 3 to 3 f1 of z dz, and we get this one as f1 of z, big f1 of z from minus 3 to 3. So here what your z value is 3 and minus 3, okay, with which you will have to substitute the corresponding things. So when you substitute these things, or if you convert this into rectangular coordinates, or with the help of x and y, you will have to do either of things. So here what I am going to do is that let me consider z equals 3, which means my r value is what? Under root 3 squared plus 0 squared, which is 3 again. Okay, for z equals minus 3, in this case also my r value is going to be under root minus 3 squared plus 0, which is 3, right? Here my theta is tan inverse of y upon x, which means 0 upon 3, I am going to get 0. Okay, that is tan inverse of 0. I will have to choose a corresponding value in this interval. Okay, here I am going to get tan inverse of what? 0 upon minus 3. So here also I am going to get the same thing, right? So here I would get 0, and here is that right? Am I doing it right? This tan inverse of 0 is to be taken as what? If we choose this also to be the same thing, we'll end up in 0, but that cannot be the case. So it is given that mm, here we have 2 upon 3, r value is what? R value is 3, so 3 to the power 1 upon 2 multiplied with e to the power, here we would get 0, I suppose. Yeah, so you'll get 0, so iota times of 0 is 0, then minus, when you substitute this quantity, yeah, from minus pi by 2 to 3 pi by 2 you have pi in between, so this may be taken as pi. So 3 to the power 3 upon 2 e to the power I 3 pi by 3 pi upon 2. Okay, here what we are going to do is that we will take this 3 to the power 3 upon 2 outside, 2 upon 3, 3 to the power 3 upon 2 may be written as 3 to the power 2 upon 2 with 3 to the power 1 upon 2, and e to the power 0 is 1, and e to the power I 3 pi by 2 is what? Cosine 3 pi by 2 minus iota times of sine 3 pi by 2. Okay, so this and this gets cancelled, so you have 2 under root 3 1, and cosine minus 3 by 2 is what? 0, and I sine 3 by 2 is minus 1, therefore you are going to get 1 plus iota. Okay, we have found this quantity. Next, in this diagram, in this contour itself, I am going to give you an exercise. Now you will have to consider like this, you will have to consider a contour C2, okay, that extends from minus 3 to 3, okay, below the real axis. So in this case what you have to do is that you will have to replace this branch. Okay, here we have considered a branch in equation 1, right? This branch has to be replaced with f2 of z, which is under root r e to the power iota times of theta upon 2 with r positive and theta to lie between pi by 2 to 5 pi by 2. You will have to take in this interval and you will have to calculate the value and you will have to complete this problem. So I leave that as an exercise to you people. Thank you.